Hello, welcome to this video. In this video, let us take one more problem on diesel engine cycle. Let us read the problem. Calculate the percentage loss in efficiency. So, we are talking about loss in ideal efficiency of a diesel engine with a compression ratio of 14. Now, it has been given to us compression ratio is 14, and we also know that compression ratio of diesel engine is little higher than compression ratio of petrol engine, where typically in petrol engine it will be 6 to 8, whereas in diesel engine it may go up to 15. And if the fuel cutoff is delayed from 5% to 8%. So, we will have to find out two cases. One is we will have to find out efficiency when cutoff is 5% of stroke. These are one case, and we will have to go for one more case, which is second case, where efficiency is to be calculated for cutoff 8% of stroke. So, these are the two cases which we will have to solve. Now, how do we start? Let us start with the PV and TS diagram. So, let us start with PV and TS diagram, which we write for diesel cycle or diesel engine. All right. So, this is what is PV and TS diagram for diesel cycle. Now, we know that cutoff is 5% of the stroke. Now, what do we mean by cutoff is 5% of the stroke? That is V3 minus V2 is 5% of V1 minus V2. So, that will write mathematically like V3 minus V2. So, that is the portion where fuel is still supplied during the expansion. All right. So, V3 minus V2 is 5%, that is 5 by 100 of stroke, that is V1 minus V2. And this we have already done it plenty of times. So, we will take V2 common here and V2 common here. So, this will be V3 by V2 minus 1 is equal to, this will be 0.05. If we take V2 here as well, we will have it V1 by V2 minus 1. So, this V2 and V2 cancels out. V3 by V2 is rho minus 1 is equal to 0.05. V1 by V2 is compression ratio R minus 1. Okay. So, the moment we see this V3 minus V2 is equal to this percentage into V1 minus V2, we can straight away write rho minus 1 is equal to 0.05 R minus 1. That is also good. Now, rho is the unknown. Let us find out the cutoff ratio, and we have been given with value of compression ratio as 14 minus 1. All right. So, the only unknown is rho. Let us find out the value of rho. Now, I will use this trick. The unknown is alpha x minus 1, or you can solve it by using equation directly. Alpha equals 0.05 into 14 minus 1, that is 13, if you directly use it. And then let us go for shift solve for x is equal to 0. Now, cutoff ratio is 1.65 for the first case. So, rho is equal to 1.65. Okay. So, cutoff ratio we have found out. For the first case, that is 5% of the stroke. Similarly, we will go for the second case, but before that let us find out efficiency. Now, efficiency of a diesel cycle is what? 1 minus 1 by R power gamma minus 1 into gamma. Here it will be rho power gamma minus 1 divided by rho minus 1. So, this will be our equation for a diesel engine cycle, ideal A standard efficiency. So, 1 minus 1 by, now what is R here? R is 14. So, 14 power gamma value for air is known to us, that is 1.4. 1.4 minus 1, this will be 0.4. I will straight away write it. Now, gamma here is 1.4. Okay. So, in the numerator, we have rho power gamma minus 1. So, rho is 1.65, gamma is 1.65 power 1.4. minus 1. So, be careful, it is not gamma minus 1, it is 1.65 power 1.4 minus 1. That answer has to be subtracted by 1. Now, rho minus 1, now rho is 1.65 minus 1. So, this must give us the efficiency for a cutoff ratio of 1.65 and compression ratio of 14, and cutoff is 5% of the stroke. That is what is important for us. Now, let us solve this. I will go with the this portion first, then I will subtract that by 1. So, numerator, otherwise I will do it in a single shot, that is also okay. So, 1.65 power 1.4 minus 1. So, let us use the bracket divided by 14 power 0.4 into 1.4 into this will be 1.65 minus 1, 1.65 minus 1. So, that will be 0.6115, 0.6115, that is has to be multiplied with 100. So, we are talking about percentage. So, 61.15 percentage. So, efficiency for a 5% of stroke is expansion stroke is where you are supplying the fuel, then we will have efficiency of 61.15%. Now, similarly, let us go for the other part, like cutoff is 8% of the stroke, then we will have the same set of equation V3 minus V2. Cutoff is 8% of the stroke V1 minus V2, and then we will take this common out here, then we will have V3 by V2 minus 1, this will be 0.08. V2 if we take out common, this will be V1 by V2 minus 1, then V2 cancels out, this is rho minus 1 is equal to 0.08 into R minus 1. Okay. Now, let us solve this equation and find out cutoff ratio. Cutoff ratio is the only unknown because we know the value of R is 14, all right. So, rho minus 1. So, alpha x, so we will start with alpha x minus 1, alpha equals 0.08 into 14 minus 1 is 13, we can straight away substitute that. Now, let us shift, solve for x is equal to 0. Then we have the cutoff ratio is 2.04. So, the value of rho is 2.04. Okay. Now, for this cutoff ratio, let us calculate the efficiency. Our efficiency equation, we have it from here, all right. So, efficiency can be calculated. Efficiency is equal to 1 minus 1 by, this is same 14 power 0.4 into 1.4, this is same. Rho is the one value which is changing from the first problem and the second sub question, all right. So, rho is 2.04 here, power 1.4 minus 1 into 2.04 minus, okay. So, therefore, can calculate the efficiency for 8% of the stroke. So, 1 minus, in the numerator we have 2.04 power 2.04 power 1.4 minus 1 divided by 14 power 0.4 into 1.4 into 2.04 minus 1. So, that is 0.59055, 0.59055. Now multiply it by 100 to get it in percentage. So efficiency is 59.055. Now we can quote the reason why this drop in percentage is, but before that let us say what has happened here. So there is a decrease in efficiency, all right. So decrease in efficiency, decrease in percentage efficiency if we increase the cutoff ratio, I mean cutoff percentage, all right. So that will be efficiency 1, that is 61.15 minus 59.055. Okay. So 61.15 minus 59.055, that is 2.095 percentage decrease in efficiency. This is decrease in efficiency in percentage. Now, why this decrease happens can be attributed from here. If you look at this portion, that is V3 minus V2 is the portion which we are talking. Now, if V3 minus V2 tells us that in total stroke, what is the percentage of volume about which we are keep on supplying the fuel. Now, if you can see that if this ratio increases from, I mean, if this value increases from 5% of the stroke to 8%, I mean, we are increasing something like this. Let us say in first case, if it is only this much, that is 5%, and in for the second case, if we increase it, so efficiency is decreased. Why that we can think of it like this. This is a portion about which we are compromising on expansion. If you keep on supplying the fuel for the remaining stroke, where do we give some time to expand or the combustion products to expand and do the work. So, we cannot go on increasing this value. Heat has to be added within that small portion of volume that will give us the better efficiency. And this can be told mathematically also. If you look at our expression, if you look at our efficiency expression, we will find out the answer why this is happening. So, if you look at this expression, efficiency expression, let me copy this efficiency expression here. So, if you look at this efficiency expression here, so we are having this term 1 minus 1 by r power gamma minus 1 into gamma. Okay. Forget about this term for now. We have here in the numerator also we have rho, and in denominator also we have rho. Okay. Let us assume that this is fixed value for now. This term is fixed value for now. Now, anything in this term is something like if we are subtracting this by 1. For example, if this is 0.1, this will be 90% efficient. If this is 0.2, this will be 80% efficient. That means this value has to be decreased in order to get higher efficiency. So, 0.1 gives higher efficiency than 0.2. This is even in ideal case is too much, but I am just quoting it for the sake of understanding. So, this value has to be lesser. Okay. When do we think that this value will be lesser? Now, if we increase the cutoff ratio, now there is rho and rho in the denominator also. Now, if we increase the cutoff ratio, this numerator also increases, denominator also increases, but please understand that this is increasing at the power of 1.4. Numerator is increasing much faster than the denominator. So, any increase in the value of rho increases the numerator. So, increase in the value of this numerator will decrease efficiency. So, we can straight away say that increasing cutoff ratio decreases the efficiency. So, increasing rho decreases efficiency. So, that is the conclusion we can make. Decreasing efficiency, increasing rho value, or in other words we are saying that the volume about which we are supplying the fuel or cutoff will decrease the efficiency. Thank you.